Okay, let's talk about orthogonal bases for subspaces. So recall, two vectors in Rn are orthogonal if their dot product is 0. Okay, let's make an example. Let's consider the two vectors in R2, the following two vectors. So u equals 2, 1 and v equals minus 2, 4. We can draw this. Okay, these two vectors are orthogonal in R2, and let's check that the dot product is 0. So we get, first note, the dot product we can always write as the transpose times the transpose of the first vector times the second vector. So we write this as u transpose times v. We now see the first one as a 2×1 matrix and the second one as a 1×2 matrix and the second one as a 2×1 matrix. So the product will be a 1×1 matrix, thus a number. Okay? So the transpose of u is the row vector 2, 1 and v is the column vector minus 2, 4. And the result is 2 times minus 2 plus 1 times 4. That's indeed 0, right? Okay. So we call u and v orthogonal. Let's write this down as a definition. So in general, two vectors u and v in Rn are called orthogonal if the dot product is 0. U and v in R are called orthogonal if u transpose multiplied with v is 0. First of all, a set of vectors, let's say a set of vectors v1 until vk, so a set consisting of k vectors in Rn, we call it orthogonal set if each two vectors, so each two distinct vectors are orthogonal. A set S consisting of vector v1 until vk in Rn is called an orthogonal set if each pair of distinct vectors is orthogonal. This means ui transpose times vj is 0 whenever I is not equals to j. So let's do an example. Let's consider the following set of vectors in R4. The set S consisting of the vectors 1, 0, 1, 1, minus 2, 1, 1, 1, and 0, 0, 1, minus 1. I claim is an orthogonal set. So let's check this. Namely, let's compute the dot product of the pairwise distinct vectors. So first let's give them the vectors names. Let's call them u1, u2, u3. Let's compute the pairwise dot product. So u1, u2 we get minus 2 plus 0 plus 1 plus 1 is 0. We can also consider u2 transpose u1, but this will be the same. So let's consider u1 transpose u3. This is 1 times 0, so 0, plus 0, plus 1, minus 1 is also 0. And it's also the same than u3 transpose u1. And last but not least, u2 transpose u3 is equals 0 plus 0 plus 1 minus 1 equals 0. Okay, so any two distinct vectors here are orthogonal. So then we have an important theorem which relates orthogonality to linear independence. Namely, any orthogonal set in Rn is also a linear independent set. Let's write this down. So let S be an orthogonal set in Rn, then it's also a linear independent set. I want to sketch a proof. Actually, I think we've done it in the class before, but let's redo it. So, what does it mean to be linear independent? So we have to consider the linear combination C1, U1 plus C2 U2 until CK UK, where C1 until CK are just numbers, and here is 0 means the 0 vector. And linear independence means the only solution for this equation of vectors is C1 equals C2 and so on equals CK equals 0. But what we can do now is we multiply from the left with the transpose of UI. So we get still 0. But now 0 is a number. Here 0 is a vector. So because the right hand side, if we multiply with UI, it's just 0. Then we get a UI C1 U1 plus UI C2 U2 plus UI CI UI plus UI transpose CK UK. I forgot there's some transposes. Now it's correct. And note the first one is just C1 times UI transpose U1. Let's assume I is not 1. If I is 1, this is 0, as it's not 0, but here is 0. The same argument holds for every number which is not I. Okay, so we get 0 equals Ci times UI transpose UI, but UI is a non-zero vector. Okay. Otherwise it would be orthogonal to any other vector. So this means this number is strictly greater than 0. Right? This is a square length of the vector. So this equation implies that Ci is 0. And it works for every I, so it shows that every Ci is 0. So our set was linear independent. And that's really the proof. Let's do another definition. Let W and Rn be a subspace. Then a basis B consisting of k vectors v1 until vk is called an orthogonal basis, provided B is also an orthogonal set. And furthermore, it's called orthonormal if each vector has length 1. It is called an orthonormal. It's called an orthonormal basis if furthermore the length of each UI, recall the length was defined as a square root of the dot product with itself, is 1 for all I from 1 to k. For example, the following 3 vectors are an orthogonal basis of R3. Okay, how do we see this? So note we only have to check that it's actually an orthogonal system, orthogonal set. Why? Because once it's orthogonal, we know it's linear independent. So it's 3 linear independent vectors in R3. There will be automatically a basis, right? Because you can have at most 3 linear independent vectors. They have to span R3, so they form a basis. So let's check it's orthogonal. So the first product gives 3 minus 1 minus 2 is 0. The second product gives 1 plus 7 minus 8 is also 0. And the last combination of 2 vectors where we can check orthogonality gives us 3 minus 7 plus 4, which is also 0. Okay? This together gives, it gives a set name S. It's an orthogonal basis of some subset, but it's R3 because it's 3 linear independent vectors, right? They span R3. In other words, there's no proper 3-dimensional subspace of R3, which is not equal to R3. Okay, let's copy this. So this is an orthogonal basis, but it's not an orthonormal basis because, for example, the length of the first vector is 2, I guess. So, but it's easy to make it an orthonormal set. So let's construct some new vectors. Let's call this u1, u2, u3, and let's define v1 to be v1 over u1 times u1. So note this is a number. Well, this is a vector, so it gives you a vector. If we compute the length of this, we get the length of u1 divided by the length of u1. So this has length 1. Let's compute the length. This is the square root of 1 square plus 1 square plus 2 square, which is the square root of 6. I was wrong before. So we get 1 over square root of 6. 1, 1, 2. Now we do the same for u2. So let's compute the length first. That's 9 plus 1 square root of 11. And let's compute for u3. The length is square root 66. Okay, and now v1, v2, v3 is actually a orthonormal basis. So it's still orthogonal, because the orthogonality doesn't change. If two vectors are orthogonal, then if we scale them, they're still orthogonal, right? If we scale them by a non-zero length. So they're still orthogonal, and they all have norm 1. So the vector we just created form an orthonormal basis of R3, okay? And now we can always do this. If you have an orthogonal basis, then we get an orthonormal basis just by dividing by the length, okay? That's all I want to talk about in the first video. Thanks for listening.